Okay, so we'll do problems today on radiation plus convection, how we can use them really in applications that are useful. So, for example, if we want to design a system using solar energy, how we can use the knowledge that we got from this chapter in order to help us into the design procedure. So I will take the following example. Solar radiation is incident on the glass cover of a solar collector at a rate of 700 watt per meter square. So this is, if you want, the solar flux that will be incident on your solar collector. Okay, so this is the value of the sun heat flux that is incident. This is what we call irradiation. The glass has an absorptivity of 0.88. So if you remember when we defined radiation, we talked about emissivity, absorptivity, reflectivity, and transmissivity. Okay? So this is for the absorptivity coefficient. And the emissivity of the glass cover is 0.9. The entire hot water needs of a family in the summer can be met by a 1.2 meters times 2 meters size collector. So here we are trying to design a solar system to supply hot water needs. This is the purpose, okay? So they are giving us the area of the collectors that we are using. The water enters the solar collector tube at a temperature of 25 degrees. Together we'll draw a small figure in order to see the components of the system. So water to be cooled has an inlet temperature of 25 degrees, and the mass flow rate of water circulating in the system is 1 kilogram per minute. The effective sky temperature for radiation exchange between the glass cover and the open sky is minus 40 degrees, and the temperature of the glass cover is measured to be 35 degrees on a day when the surrounding air temperature is 25 degrees. So we have a lot of information. This is why we can, if you want, try to organize the information. So concerning the waters that we want to heat, we know the temperature, the inlet temperature is 25 degrees. So this is TW in. 35 degrees is TW out. So knowing, if you want, the inlet temperature and the desired outlet temperature, in addition to the mass flow rate, we can determine what is the useful heat, okay? Because water will extract heat from the solar collector, and Q dot extracted by water, we know already that whenever we have, let's say, a liquid or a solid passing by taking sensible heat, the sensible heat can be calculated as mCp delta T. And if we want to calculate a rate, this means that we want to get it in joule per second. All we have to do is to multiply the mass flow rate m dot times the specific heat Cp times delta T. So here we have everything about water. We know what are our needs. So we want to design accordingly the solar collector that will supply our needs. Wind flows across the 2-meter surface at an unknown velocity u wind. So in this problem, based on the design, we need to determine what was the value of u wind that, if you want, gave us an area of 1.2 times 2 meters. In general, in the design, you know the wind velocity, and you will decide on the area or the number of collectors to use, number of PV panels to use, okay? So assume the back surface of the absorber plate to be heavily insulated, and the only heat loss will occur through the glass cover of my collector. The collector efficiency, which is the ratio of the amount of heat transferred to the water to the solar energy absorbed by the collector, is given to be 20.4%. Let us look at a representation of our system. So this is our house. We know what are the hot water needs, okay? And of course, the hot water needs will depend on the number of persons will depend on the lifestyle. You know that the number of shower per day will affect, let's say, m dot that you need, etc. So we need to know all of these informations in order to decide on the amount of heat required. And then based on this, they gave us the mass flow rate, the specific heat, and the value of delta T. Now, as we can see in this figure, we know that the surface temperature, so we have a certain temperature of the solar collector surface. This temperature is provided. They told us that T glass is equal to 35 degrees. We know also what are the conditions. So we have T inlet and we want to look for T out. Okay. So here T out is unknown. 35 was not the outlet temperature, it's the glass cover temperature. So they didn't give us here T out, but we will be able to calculate it from the energy balance equation. Okay? So we don't know T out. We want to do a calculation to determine this value. Plus, we know that the solar collector is exchanging heat through the glass cover only, because they told us that it's well insulated from all sides. So here, this is the symbol of, if you want good insulation. So we don't have heat dissipations through these walls. And just this collector will exchange heat through the glass cover. Plus, of course, this heat, the heat absorbed, yani the net heat absorbed, will be delivered to water. Now, the first question was to determine the outlet temperature of the water. So just please fix this. This is the temperature of the surface, okay? And T water out is to be calculated. So to be able to calculate TW out, we should ask ourselves, what is the source of this energy? Okay, we know that the source of energy that will increase the temperature of water is the amount of solar energy that will really reach water. Okay, this is why they told you that we have a certain efficiency for our system. And this efficiency seems really low because of high losses. Yani it's true that we have only losses at the glass cover level, but these losses are considerable because we have conduction, we have also radiation, plus, of course, here you have water circulating, so you have a certain efficiency for the heat exchange. So this is why in overall, only 20%. Guys, please can you mute your microphones? So only 20.4% of the absorbed energy will be really transmitted to water. Okay? And they define for you this efficiency. So we can write that this efficiency, which is the collector efficiency, is equal to the useful heat. The useful heat, Q dot useful, is the one used by water. So this is the sensible heat that will lead to increase in the temperature of water over what is absorbed by the solar collector. Okay, the solar energy absorbed by the collector. Now, we know that the flux of the sun is 700 watt per meter square. And first, to get it in watt, we multiply by A. So this will be the rate reaching the glass cover. But you know that only a portion will be absorbed. This is why they gave us the absorptivity. So now we'll use the absorptivity given in order to calculate Q dot solar absorbed. And now all we have to do is to replace in this equation. So if we replace, we have m dot of water times Cp. Cp of water is given for you, of course. So here you have the specific heat of water. You don't have to memorize anything. And just pay attention for units. You know that whenever Q dot is in watt, your mass flow rate should be in kilogram per second. your specific heat is in joule per kilogram Kelvin, so you put it as it is. And you have times delta T, which is T out minus T in. Now, we don't know delta T, but we'll see that the only unknown in this equation is T out. So from this relation, we'll be able to calculate T out. So over Q dot absorbed. Q dot absorbed is alpha, which is absorptivity, times the area, times the solar flux GS. So we have the area of the collector. The area of the collector is 1.2 times 2. And alpha is 0.88. And GS is 700. So we will be able to calculate delta T. Knowing all parameters, we get the value of delta T. And delta T represents T water out minus T water in. Okay? So from this equation, you will be able to calculate what is the outlet temperature of your water. And of course, in case you know that, for example, let's say for shower, we need to reach water temperatures above 70 degrees in order to kill some types of bacteria. So in case you got a value lower than the one desired, you should, for example, decrease the mass flow rate, because for the same Q absorbed, okay, if you want to increase delta T, you need to reduce m dot. So this is why you will need more time if you want to heat the quantity needed. So in general, this is why we do design previously in order to decide on the corresponding area in a way to get hot water in a short amount of time. Okay. So now this is how we can calculate the value of delta T. Okay. Now, next step, we want to find what is the wind velocity. Okay. And here in this problem, as I told you, everything needed will be given for you in the exam. So here, I gave you notes. So I give you some formulas that you will need. We told you that for laminar flow, the Nusselt number, which is the convective coefficient times the length over K, is function of the Reynolds number and the Prandtl number. The Prandtl number is also a characteristic of the fluid, and here it's given for you. Okay. While if you have turbulence, the Nusselt number will have a different expression. And since I gave you the two expressions, so you are not sure if your flow is laminar or turbulent. That's why you need to do like an assumption. So you say, assume it laminar. If it's laminar, your Reynolds number should be smaller than 5 times 10 5. Also, I don't consider that you know what is Reynolds. So you have here, I gave you what is the Reynolds number. Okay, so the Reynolds number will be given for you as a formula. So the Reynolds, okay, is the velocity of wind times the characteristic length over the kinematic viscosity. So this formula also will be given to you. Okay, then all you have to do is to apply these formulas accordingly. Okay, now U wind, as you can see, is related to Reynolds. And from the equation they gave us here, Reynolds is related to the Nusselt number, which is related to the convective coefficient. So from here I should say the next step will be to try to find what is the convective coefficient. And please always, in such a problem, think about the energy balance. Because in heat transfer, always you will need to write a balance of energy in order to find your unknown. Okay? So all I have to do now is to do a small figure illustrating all the processes that are happening. Okay? Let me consider my solar collector. So if I consider my solar collector as my system, okay, I will represent all the exchange between my solar collector and the surrounding. First, I have, as you know, the flux from the sun, okay? And we said that we can calculate it as alpha times area times GS. So this will give us the rate that is absorbed by our collector. Now, They told us that we have good insulation here, so no heat dissipation from these sides. So of course, you only have heat towards water, okay? Because water will take part of this energy. So you have Q dot water that we already calculated. يعني now we know what is Q dot water, which is, or you can say, or it's M dot Cp delta T. Or also, since you can calculate it using the efficiency, so it's equal to the efficiency of your solar collector times alpha times A times GS. Now, what about the remaining part? What about the remaining part of energy? It is exchanged with what? Who can tell me? You have here loss of heat through your glass cover, okay? They told you that you have convection with air, because if you go back to the figure, you have air, air that is blown over because of wind. You have air blown over your surface. So this will lead to heat dissipation by convection. Okay, so first I should illustrate the convective flux getting out, plus also I have radiation flux. Okay, and to get it, you know that for radiation, you should consider the net radiation. The net radiation, which is, if you want, equal to the emitted flux minus the absorbed one. Okay, and you know we have formulas to get these. So first, whenever you consider emission from the glass cover, you have to consider the value of epsilon. Epsilon is given for you. And then you consider, since it's emitted from the surface, you will use the temperature of the surface. While for the absorbed one, they told you that the effective sky temperature for radiation exchange between the glass and the open sky. So if you want, you have radiation coming from the open sky, which has a temperature of minus 40 degrees. So now when you consider the absorbed radiation coming from sky, you need to consider the temperature of the sky, and of course you need to consider the absorptivity. Okay, in the course material we said if they don't give alpha, we take alpha equal epsilon. But if they gave you alpha different than epsilon, you should know where to use epsilon and where to use alpha. So now, next step will be to illustrate these fluxes, these rates of heat in our figure. So we have Q convection out, and this Q convection out is calculated as H times A times T surface minus T infinity, which is T of air if you want. And for the radiation, for the net radiation out, okay, for net radiation out, you have that Q net radiation is equal, so as we said, it's the emitted minus the absorbed, and it is equal, then the emitted is epsilon times A times sigma times T surface to the power 4, and don't forget to use the temperatures in Kelvin, minus alpha times the area times sigma times T sky to the power 4. Okay, and now you are done with the representation of all of your fluxes. So all you have to do now is to write the energy balance. You know that whenever you have a system at steady state, summation of fluxes coming in equals to summation of fluxes getting out. So all you have to do now is to say sum of Q dot in equals to sum of Q dot out okay, and then what do we have as inlet? The only inlet is if you want the absorbed flux from the sun. So alpha times A times G sun equals to, we have the convection, so H times A times T surface minus T air. This is the flux lost. This is the flux lost by convection plus the net flux lost by radiation, which is A times sigma times epsilon T surface to the power 4 minus alpha T sky to the power 4. And as we said, don't forget to put in Kelvin. So T sky is minus 40, okay, plus 273, so it's 233 Kelvin. While your surface is at a temperature of 35 degrees, so 273 plus 35, so here it's 308 to the power 4. And finally, you have the heat, the useful heat that is used by water, so plus Q dot water. And if you look at your parameters, you know everything except the convective coefficient. Alpha is 0.88. A is the area. They gave us 1.2 times 2. We know the area. This is 700 watt per meter square. T surface is 308 Kelvin. The temperature of air is 25 degrees, so 298. The Boltzmann constant will be given for you. It is 5.67 times 10 minus 8. Epsilon is also given. It's equal to 0.9. And Q dot water was already calculated. Okay, it's equal to the efficiency times alpha AGS. So now you replace all your numbers. The only unknown is the convective coefficient. You get the convective coefficient. Now, what we need to find is the velocity of air. Okay? And as we said, the velocity of air is directly related to the Reynolds number. So the strategy is the following. Since now we know the convective coefficient and we know the length L of our solar collector and we know the conductivity of the material, so we can calculate the Nusselt number. But we are not sure if the flow is laminar or turbulent. Because if it's laminar, we have a function relating the Nusselt and Reynolds. And if it's turbulent, we have a different relation. So to know which one to use here, we are forced to do an assumption. Okay? Since you are not sure, you say, let me assume. You can do the assumptions that you want. You can assume laminar or you can assume turbulent. And once you do your calculation, you should verify your assumption. What do we mean by this? So let's say you consider the flow laminar, okay? You replace Nusselt by HL over K, you calculate Nusselt. And based on this, you have everything. Prandtl number is given for you, it's here in the given. It's 0.706. K is also given, you have everything. So you will be able to calculate your Reynolds number. Okay, but now you can check for the assumption, because for this equation to hold on, you should have that the Reynolds should be smaller than 5 times tan phi. If you get it larger than 5 times tan phi, you say my assumption was wrong. Let me use now the right relation. Nusselt number is already calculated, but use now this relation to get the Reynolds number. And of course now, it will be a number larger than 5 tan phi, because if this is wrong, this will be true. Okay? So let us recap. So the first step was to find the temperature at outlet using the efficiency definition. The efficiency of the collector is Q water used, which is the useful energy, over the one absorbed by the solar collector. once we have it, we can write the surface energy balance. So as we said, that here, if you want, instead of writing all terms in watt, they did it in watt per meter square. So they divided everything by the area. Okay, so it's equivalent. So the area is the same everywhere, and here you will have Q water over A if you want to use an equation of unit watt per meter square. And when they replaced all numbers, they got the coefficient H. Next step is they calculated the Nusselt number, and now is the time of the assumption. So if you do the first assumption of considering laminar flow, you get a Reynolds number larger than 510.5. So you say my assumption is wrong. And now you repeat, you take the other formula and you get Reynolds. You get as expected now, you get a Reynolds number larger than 5 times 10 to the power 5. So now you know what is the Reynolds number. You are ready to use the equation, which is Reynolds is velocity times L over mu. Okay, this is the kinematic viscosity. The kinematic viscosity is the dynamic viscosity over rho. But don't worry, I don't consider that you know any of these. All relations will be given to you. Just you should know to write the energy balance and to use the empirical relations in an appropriate way. Okay? Any question on this problem? Okay. We'll do now together another problem. Another problem of interest can be to optimize insulation. Sometimes we need to come up with the design of a certain system with maximum insulation, and other times we need to have minimum insulation. So it depends on the configuration. If we want to have heat exchange, high heat exchange, we want minimum insulation. And if we want to reduce the heat exchange to the maximum, we should have maximum insulation. So this is an example to see how we can do the design procedure. A thin-walled copper tube of radius Ri is used to transport a low-temperature refrigerant that is at temperature Ti and is less than that of the ambient air, which is at T infinity around the tube. Is there an optimum thickness associated with application of insulation to the tube? So we want to check if we can find a certain insulation that will maximize or minimize, because when we say optimum thickness, we didn't mention if it's maximum or minimum. Okay? If we say, here's I said insulation, okay? Because I said insulation, so the purpose, let's say, is to have good insulation, then we should have a maximum. So here, because they related it to high insulation, this should be, the optimum should give us maximum insulation, okay? But on the other hand, if they just talking about an optimum thickness without, if you want, telling us that that we want to have good insulation, it can be or maximum or minimum insulation, and this depends on the application we are using. So now in this problem, we'll see from calculation if it's possible to maximize insulation or not. So, and after we do the analysis, we will verify this by doing calculation for a 10 millimeter diameter tube having the following thickness: 0, 2, 5, 10, 20, and 40 millimeter. And they told us that the insulation is composed of cellular glass, and the outer surface convective coefficient is given to be 5 watt per meter square Kelvin. So again, one of the main application of conduction is to have good insulation. And you know that we studied in the course material what is, let's say, the total resistance associated with plane wall. And also I told you that in case I don't give you a plane wall, I will give you what is the formula of resistance. So we already know that for plane wall, the resistance to conduction is given by K times L. Sorry, it's the inverse, L over Ka. okay? Because you need to, you know that when you want to resist to conduction for a wall, you should increase the thickness, okay? And you should reduce the conductivity and reduce the area of transfer. So this is if you have a plain wall, okay? Now here you don't have a plain wall, you have a circular wall. So I will give you the formula, okay? So we will tell you what is the form of resistance. So the resistance associated with a cylindrical form, okay, is given by ln of the outer radius R2 over R1 divided by 2 pi times the conductivity times L. Okay? So this will be provided for you. And here we want to let's say we want to see if we can maximize insulation. Okay? So to have a maximum insulation, this means that the resistance to heat is maximum. And as you can see in this figure, you have conduction through the wall, your cylindrical wall, and from outside you have convection. Okay? This is why, as we used to do in the course material, okay, we can build by analogy, an electrical circuit, but now we consider that the voltage is equivalent to temperature and the current is equivalent to heat flux. Okay? So if we draw this circuit together, we have first, let us zoom a little bit. So initially we have, at the inner side, we have the temperature of the inner surface. Okay? And from the other side, from outside, we have T infinity. And as I told us, the temperature T infinity is larger than T inner. Because of this, we know that heat will always go from hot to cold side. So the heat flux will be in this direction, from T infinity to T inner. And the resistance to convection is 1 over H times lateral area of our cylinder. Here, what is in contact, the area in contact with air, if I illustrate the cylinder, okay, as you can see here, this area will be in contact with air. So the lateral area is the length of my cylinder times the perimeter, which is 2 pi r. Okay? So this is equal to 1 over h times 2 pi r times the length L. Okay? 2 pi r times L. And we have seen together that for the cylinder, the resistance is, for conduction, the resistance is ln outer radius over inner radius over 2 pi kl. Now, since you have L in both, L can be simplified. You have L here and you have L here. So if you want to do the analysis per unit length, so if you want to put resistance per unit length corresponding to unit length, you remove L and you remove L from here. And then instead of having the rate in watt, Q prime, you will have Q prime in watt per meter. So if you remove L, you will consider the flux in watt per meter. Okay? Now, our purpose, as we said, is to optimize the resistance. So we can say that our total, the total resistance here that we have, is the summation of, you know that whenever you have resistances in series, the total resistance will be the summation of both. So R prime, if you want, which correspond to unit lengths, is ln R outer over R inner over 2 pi k plus 1 over 2 pi R h. So as you can see, the radius has opposite effect. If you increase the outer radius, this will increase the resistance to conduction. But at the same time, if you increase the outer radius, this will reduce the resistance to convection. Why? Because you will have a larger area of exchange. This is why the convective heat will increase and the resistance will decrease. Okay, so we can see here that R has opposing effects on the total resistance, and that's why we need to determine if we have, let's say, a maximum or a minimum. So to know this, it's math. Yeah. Now all we have to do is to derive, because to find if we have an optimum, we should say that the derivative of R prime with respect to R should be equal to 0. And here the functions are not complex, we can easily derive. So if you derive this equation, you will get that 1 over 2 pi kr minus 1 over 2 pi r square h should be equal to 0. And this will give you a radius k over h. But now, how we can check if this is a maximum or a minimum? You know also that to get a minimum, the second derivative should be positive. And to get a maximum, the second derivative should be negative. So now we should check for the sign of the second derivative. So if we derive this equation again, and we replace the optimum, which is R equals K over H, we get that for this value, the second derivative is positive. This means that we don't have a maximum, we have a minimum. So we can say from this study that whenever we have a cylinder, we can select a radius that minimize insulation. So this radius will allow for maximum heat transfer. And this can be used in case you have an application requiring to maximize the heat transfer. On the other hand, if you want to increase insulation, the only way will be to increase, yani, as you increase R, the insulation will be better, because when you go to infinity, if R tends to infinity, so as R will increase, the resistance will increase. This is why we don't have a maximum, because it will tend, the maximum will go to infinity. And from here, but we know that we have the economical constraint, and we cannot increase a lot the radius because of cost and because of space limitation. So then you say that the more I increase the radius above R critical, I can insulate more. Okay? So this is how you can answer this question. And you can verify this, okay, in this problem, you can verify this by doing a small drawing. If you draw the variation of the total resistance, you will detect the presence of a minimum. And then as you go away from this radius, your total resistance will keep increasing. Okay? Any question on this? Okay. Thank you.